SiMWiSense. Simultaneous multi-subject activity classification through Wi-Fi signals. This novel approach addresses the challenges of generalization and scalability in Wi-Fi sensing systems, which are highly dependent on the subject and environment. SiMWiSense classifies activities of multiple subjects using channel state information, CSI, from Wi-Fi devices positioned closest to each subject. To tackle the scalability issue, multiple Wi-Fi devices are utilized as CSI collectors. The device closest to a given subject is used for classifying its activities. Experimentally, it is proven that the device closest to the subject dominantly characterizes the channel property between itself and the source of the Wi-Fi signal. The task of finding the closest device to a subject is considered out of the scope of this research, as it falls under Wi-Fi indoor localization and/or fingerprinting. To address the generalization issue, a brand new few-shot learning algorithm named Feature Reusable Embedding Learning (FREL) is developed. FREL can adapt to any new environment, significantly changing its performance with new untrained environments and subjects. The proposed FREL architecture improves the accuracy of the classifier output, making it more efficient and adaptable. SiMWiSense experimentally achieves a classification accuracy of up to 97% using the FREL algorithm. FREL improves accuracy by 85% compared to a traditional convolutional neural network, CNN, and up to 20% compared to the state-of-the-art few-shot embedding learning, FSEL, using only 15 seconds of additional data for each class. The authors share their 1 terabyte dataset and code repository for reproducibility purposes. SiMWiSense is a significant contribution to the field of Wi-Fi sensing and its applications, achieving high classification accuracy and improving upon existing methods. The SiMWiSense framework, proposed in this research, is designed to classify multiple human activities simultaneously using Wi-Fi sensing. It addresses the challenges of generalizing to new environments and subjects through a novel feature learning approach called Feature Reusable Embedding Learning (FREL). In the context of multi-subject simultaneous activity classification, the proposed FREL architecture utilizes metalearning and fine-tuning to adapt to new environments and subjects with minimal additional data. The authors evaluate the performance of SiMWiSense through an extensive data collection campaign in 3 different environments, involving 3 subjects and 20 different activities. A sensing proximity test was conducted to assess the feasibility of using channel state information, CSI, monitors to capture changes in the propagation channel between the access point, AP, and the monitors. The test involved assigning a CSI monitor to each subject, placed at varying distances, while a human subject performed activities near the monitors. Results show that the CSI monitor closest to the subject achieved the highest classification accuracy, supporting the key concept of spatially distinct monitoring. A critical analysis of this sensing proximity test can be understood as captured CSI dominantly characterizes the changes in the propagation path caused by subjects spatially closer to the corresponding CSI monitor. By extensively analyzing, thus found result reveal compelling improvement achieved when in similar configuration condition set activity when over benchmark reach much competitive position up on simple non-training existing competitive best that yield gain comparable SiMWiSense overall scheme devised solution efficiency higher noise sensing low using passive monitor class wise single distinct setting show promise such prior test given accurate capturing signals performed set particular as used study testing monitor prior subjects performing many movement this experiment's SiMWiSense adaptive spatial accurate position identification wise provide highest this configuration accurate time perform required result state over network train accurate scheme only thus present outperforms CSI traditional such capturing reaching proposed existing required SiMWiSense analysis phase multiple many devices higher quality proposed here quality all testing classification monitoring systems on robust comparison Wi-Fi use even systems achieve up quality both tested 3 main existing low complex space as network condition improve several sensor settings. SiMWiSense is a proposed system comprising sensing and preprocessing blocks, followed by a learning block. The sensing block collects channel state information, CSI, of Wi-Fi transmissions using orthogonal frequency division multiplexing, OFDM, modulation. The CSI matrix, N, is extracted, representing the CSI matrix at receiver R of the transmit antenna M and receive antenna N, with dimensions S times K, where S is the number of samples and K is the number of orthogonal parallel subcarriers. The preprocessing block aligns the collected CSI data by discarding missing or corrupted measurements, normalizes the data by removing abrupt amplifications, and segments the captures into fixed-size non-overlapping windows along the time domain. Each window has a tensor dimension of SP times K times N, where SP is the number of samples in the PTH time window, K is the number of OFDM subchannels, and N equals 2 is the complex CSI measurement. To address the challenge of scalability in multi-subject detection, the learning block proposes a decentralized detection system, where each subject is assigned a learning model to sense the closest subject. Reducing overall complexity from O, QP, to P times QA cascaded model is also proposed for two-stage detection, consisting of a coarse detection stage that discriminates different subjects and a fine-grained detection stage that determines the activities. This approach further reduces the complexity to P plus Q. The cascaded model enables efficient multi-subject detection, while minimizing computational overhead. The FREL model, a novel fusion of embedding learning and metalearning, enables swift adaptation to new scenarios with limited data in Wi-Fi sensing applications. This model consists of two primary components, an embedding network and a classifier. The embedding network projects input data into a latent space, while the classifier decodes the features within this space. By training on a merged dataset comprising multiple tasks, the optimization problem is reduced to a general deep learning problem, solvable using gradient descent. During the metalearning phase, the embedding network and classifier are jointly trained on a mini dataset. Once the optimal embedding is obtained, the classifier is fine-tuned on a small portion of data, involving random sampling of K shots from each of N ways in the tuning dataset to build a new task. The classifier is updated via gradient descent. Performance is evaluated on the remaining unseen dataset. The SiMWiSense learning block employs a DNN architecture for the embedding network, comprising 4 convolutional layers with batch normalization and ReLU activation, followed by 2 fully connected layers with ReLU activation and a final softmax layer for output. Each convolutional layer uses a 3x3 kernel size and 2x2 stride. The FREL model offers significant advantages over traditional approaches, including improved adaptability to new subjects and channel conditions, and reduced computation requirements during fine-tuning. This model has the potential to substantially enhance the efficiency and accuracy of wireless sensing systems, particularly in scenarios where data collection is challenging. The proposed FREL model introduces a novel approach to learning reusable features in wireless sensing, comprising 2 phases, metalearning and fine-tuning. This model utilizes a convolutional neural network, CNN, as the embedding network, which consists of 4 convolutional layers followed by a global average pooling layer. Each convolutional layer has 64 channels, a kernel size of 3x3, and uses ReLU activation and batch normalization. The CNN is trained using cross-entropy loss with an atom optimizer and a learning rate of 0.01. The Feature Reusable Embedding Learning algorithm involves initializing the embedding and classifier parameters, then updating them through the metalearning and fine-tuning phases. In the metalearning phase, the model updates the embedding and classifier parameters based on the provided dataset. In the fine-tuning phase, the model updates the classifier parameters using a mini dataset, which contains limited tasks and samples. The evaluation of the FREL model is conducted in 3 different environments: classroom, office, and kitchen, with 3 human subjects performing 20 different activities. The experimental setup includes off-the-shelf routers for setting up the network and ASUS RTAC86U routers with Nexmon tool for extracting the channel state information, CSI. The access point and stations are configured with 3 antennas and 3 spatial streams. The mini dataset used for fine-tuning contains a limited number of tasks and samples, making the problem more challenging for the model. The FREL model is compared to a state-of-the-art FSEL model, which uses a k-nearest neighbor, KNN, algorithm as a comparison. The KNN algorithm is implemented after the metalearning phase, following the same procedure as the FREL model. During inference, K-samples from each class are transformed into embeddings as supports, and the queries are classified by a plurality vote of the K-nearest supports. Overall, the FREL model demonstrates the effectiveness of learning reusable features in wireless sensing tasks, particularly in scenarios where new tasks are constantly emerging due to changing environments. The experimental setup for evaluating SiMWiSense, a Wi-Fi sensing system for simultaneous multi-subject activity recognition, consists of 3 CSI monitors placed in a classroom, office, and kitchen, with 3 subjects performing 20 different activities. CSI data is collected at a center frequency of 5.21 GHz with 80 MHz bandwidth, and 3 separate models are trained for each monitor using data from each subject. The performance of SiMWiSense is evaluated using a 2-stage detection system, comprising subject identification and activity classification. For subject identification, a baseline CNN model achieves an average accuracy of 95.47%, 96.68%, and 97.34% for monitors 1, 2, and 3, respectively, across all 3 environments. The results show no significant performance discrepancy between the monitors, but a 3.51% performance boost in the office environment due to less noise in identifying the closest subject. For simultaneous multi-subject activity classification, the baseline CNN model achieves an average accuracy of 98.51%, 97.37%, and 97.49% in the office, classroom, and kitchen environments, respectively. The performance discrepancy between the monitors is less than 2%, demonstrating the stability and robustness of SiMWiSense. The authors also investigate the impact of subcarrier resolution on SiMWiSence's performance, showing that the system's performance decreases with lower subcarrier resolutions. However, the results suggest that SiMWiSense can still achieve high accuracy with a reasonable subcarrier resolution, making it a promising solution for Wi-Fi sensing applications. Here's a direct and concise voiceover script based on the text. Research evaluated the SiMWiSense sensing system across varying environments: classrooms, offices, and kitchens, along with assessments of performance using a different number of subcarriers. Figure 12 data indicates that SiMWiSense achieves high accuracy in all environments when using a baseline CNN model. In the classroom environment, Figure 13 shows that decreasing the number of subcarriers leads to decreased average performance, dropping significantly at 20 subcarriers. Confusion matrices for 242 and 20 subcarriers, presented in Figure 14, underscore the challenges in distinguishing certain activities with reduced subcarriers. Further evaluation was conducted to assess the performance of SiMWiSense using FREL, a feature representation learning approach, in new environments without prior training. Figures 15 and 16 demonstrate FREL's superiority in generalizing to new environments and subjects compared to traditional CNN and FSEL, with improved overall performance of 86.06%, 87.56%, and 86.90%. Figure 17's confusion matrices illustrate FREL's advantage over FSEL when trained with monitor M1 in the classroom and tested with the same monitor in the office. Notably, the top 3 activities that FSEL found difficult to distinguish were pinpointed, highlighting FREL's robustness and reliability in untrained environments. This section of the research paper presents a comparative analysis of the proposed FREL model's performance against traditional CNN and FSEL models in various environments. The results indicate that FREL significantly outperforms both CNN and FSEL in terms of accuracy, particularly when tested in new untrained environments. A comprehensive analysis of FREL's ability to generalize subject identification across different environments is presented, demonstrating its stability and reliability in this phase of the learning process. It also highlights FREL's capability to adapt and generalize to other monitors, reducing training time and deployment complexity. An overview of related work in Wi-Fi sensing is provided, emphasizing the significance of the proposed model in the field. Overall, the findings suggest that FREL is a robust and efficient solution for Wi-Fi-based activity recognition systems, offering superior performance and adaptability compared to existing models. In the realm of Wi-Fi sensing, the FREL algorithm's performance with new untrained monitors is presented in Fig. 20, showcasing its adaptability to novel environments. This work contributes to the growing field of Wi-Fi sensing, which has been explored through various approaches, including RSSI-based methods and passive Wi-Fi radar (PWR). However, channel state information (CSI)-based Wi-Fi sensing remains the most popular approach, with deep learning (DL) models achieving remarkable results in various applications. DL has been effectively employed in human activity classification, gesture recognition, health monitoring, and indoor localization, among other applications. The work by Shalabi et al. Demonstrated high accuracy, up to 99.46%, using various DL models, including CNN with gated recurrent unit, GRU, and long short-term memory, LSTM. However, these models were limited to single-subject scenarios and struggled to generalize to new environments. Wang et al.'s MCBCAR used generative adversarial networks, GAN, and semi-supervised learning to address the challenge of non-uniformly distributed data due to environmental dynamics. The AFSL-HAR framework achieved a performance gain in recognizing new activities with few new data samples through few-shot learning. Ding et al.'s WiLA-sensing and RFNet addressed variations in activity locations and environments, respectively. This paper proposes the SiMWiSense framework, which leverages CSI-based Wi-Fi sensing for simultaneous multi-subject activity recognition. SiMWiSense surpasses traditional CNN-based approaches and state-of-the-art few-shot learning models by 85% and 20%, respectively. The framework consists of an FSEL-based algorithm, FREL, which enables fast adaptation to changing data distributions and achieves an accuracy of up to 98.94% in new environments and subjects. The results demonstrate the effectiveness of SiMWiSense in real-world scenarios, including classroom, office, and kitchen environments. This work contributes to the field by providing the first framework for simultaneous multi-subject activity recognition with Wi-Fi sensing. The results have implications for various applications, including healthcare, education, and smart environments. Future work should explore further refinement of the FREL algorithm and the development of new CSI-based Wi-Fi sensing applications. Limitations include the assumption of availability of labeled data and the requirement of multiple monitors for robust sensing. Overall, this research provides a comprehensive analysis of the current state of Wi-Fi sensing and demonstrates the effectiveness of the SiMWiSense framework for simultaneous multi-subject activity recognition. It seems that there is no content provided for me to refine. Please provide the research paper transcript, and I'll be happy to help you refine it according to the guidelines. I'll transform the text into a direct, concise form suitable for voiceover narration, maintaining technical accuracy and depth while ensuring no loss of critical information.